Hello everybody. Let's discuss theorem today. Okay, let's take a break from discussing the strange math problems I usually find on Facebook. Let's talk about one theorem in this video, and it's one of the most popular concurrency theorems related to triangles in Euclidean geometry. Okay, and I'm going to explain the concepts of in-center and in-circle in just a moment. For that, we need to discuss this theorem. Okay, the internal angle bisectors of any triangle are concurrent. By internal angle bisectors, we mean the bisector of this angle, the bisector of this angle, and the bisector of this angle. Okay, internal angle bisectors. Now, to show that they are concurrent, let us suppose this is the bisector of angle Q. If this is alpha, then this is alpha. Okay, and let this be the bisector of angle R. This is any triangle PQR, and I'm not considering the cases where one of the angles is right angle or right angled or obtuse angled, or all of them are, or the case that it's an acute angle triangle, because it's not going to matter in this case. In other concurrency theorems, that'll play a crucial role, but not in this one. This is the simplest concurrency theorem. Okay, this is the simplest one. Okay, now this is the bisector of this angle. So if this is beta, then this will be beta. Okay, now we need to show that the bisector of angle P. Okay, we need to show that the bisector of angle P passes through this point, let's say I. Okay, we want to show that bisector of angle P. I'm not going to write the complete proof. Okay, I'm just going to write the main points. Passes through I. Now, just for the sake of contradiction, okay, for the purpose of contradiction, let a bisector of bisector of angle P does not pass through I. So want to show, it's really rough. Okay, let want to show doesn't hold, means this doesn't hold. So the bisector of angle P does not pass through I. Okay, now we'll see that this assumption leads us to a contradiction. Okay, as a result of which the theorem will be proved. Now, join P and I. We can join P and I whether or not the bisector of angle P passes through I. Okay, let's join P and I, and let us draw IX perpendicular to PR and IY perpendicular to IY perpendicular to IY perpendicular to IY perpendicular to PQ, and IZ or IZ perpendicular to RQ. Okay, this point is I. This point is I. Now let's see this part. I've discussed this part so many times, I guess. Okay, this is right angled. This is right. This is right angled. Y, Q, I and Z. Yeah. And this is alpha, this is alpha. One pair of angles, they're equal. Two pairs of angles are equal. There's a common side, means a pair of sides in these two triangles are equal, as a result of which these two triangles are congruent, and since the corresponding sides of congruent triangles are equal, this side will be equal to this side. Okay, so this side is equal to this side. Similarly, if you look at this part, one pair of angles, they are equal. Two pairs of angles, they are equal, and there's a common side. So a pair of sides are equal in these two triangles, as a result of which these two triangles are congruent. And since the corresponding sides of congruent triangles are equal, this side will be equal to this side. As a result of which, we see that Ix is equal to Iy. Now, let's look at this part. Look at this part. This is 90. This is 90. This is P, this is I, this is X, this is Y. Okay? Now, these two are right angle triangles. A pair of legs are equal. Okay? And the hypotenuses, the two hypotenuses, they're equal because the hypotenuse of this triangle is the hypotenuse of this triangle. In other words, it has a common side which happens to be a hypotenuse. So in a right angle triangle, two pairs of sides are equal. This is equal to this, this is equal to this. So the two triangles, they are congruent, as a result of which corresponding angles of congruent triangles, they are equal. So this angle is equal to this angle. So if I suppose this is theta, and this is also theta. So if this is theta, then this is theta. Okay. Now we can see that the line joining P and I is a bisector of angle P. Okay. We see that the line joining P and I bisects angle P. Okay, bisects angle P. So PI is a bisector. That is, PI is a bisector of angle P. So this is a bisector of angle P. But we have assumed that the bisector of angle P does not pass through I. So the bisector of angle P, as per our assumption, this is a bisector of angle P. Okay, PP dash is a bisector of angle P, which does not pass through the point I. As a result of which, we have two bisectors of angle P. Two bisectors of angle P, which is absurd. So we arrive at a contradiction. So with this assumption that the bisector of angle P does not pass through I, we have arrived at a contradiction. So this assumption is false, as a result of which this is true. Whatever we wanted to show is true. So we've proven this theorem by the method of contradiction. Okay, as a result of which the internal angle bisectors of a triangle are concurrent. So basically, two lines either intersect or are parallel. If this is parallel, if any line parallel to QI will not bisect this angle, as you can see, okay, as you can see, so they must intersect, and it will be inside the triangle, because outside of the triangle we need to bisect the angle inside the triangle. If it's outside, then I don't know, it won't intersect. Okay, it will be somewhere here, somewhere here. So extending this side, it won't intersect at all, so it must intersect inside the triangle. Okay, it will always intersect inside the triangle, and this is the intersection point of these two bisectors. And since this bisector, the bisector of angle P, also passes through I, since three lines pass through the same point, we say that the bisectors, these bisectors, which are the three lines passing through I, are concurrent. Okay, concurrent means if three or more lines pass through a single point, they are said to be concurrent. Okay, all right, so theorem holds. And these two concepts, now make a quick observation. From the incenter I, the distance, the sides of the triangle are equidistant. Okay, this Ix is equal to Iy is equal to Iz. So we take a note of that fact as well. Now let's see. Now let's discuss two concepts. Incenter, point of concurrency, of the internal angle bisectors. Okay, so if this is the intersection point, okay, the point of concurrency of the angular bisectors is I, and we call this point of concurrency as the incenter of triangle PQR. Okay, and we've just noted the fact that if I is the incenter, in the previous proof it was quite evident from the previous proof that if I is the incenter, then it was Y, I guess, Ix Ix is equal to Iy is equal to Iz. So if this is R, this is R, this is R, then taking I as a center and R as a radius, we can construct a circle through X, Y, and Z like this. As a result of which, since this is perpendicular, this will be a tangent. Okay, this will be a tangent, this will be a tangent. PR is a tangent to this circle at X. QR is a tangent to this circle at Z. PQ is the tangent to this circle at Y. Alright, we can construct a circle like this. Okay, we can construct a circle like this, as a result of which we can construct a circle like this, and this circle whose center is the incenter of the triangle PQR, okay, circle whose center is the incenter of the triangle PQR, this circle will be called the incircle of triangle PQR. Incircle of triangle PQR. Okay, I think it's clear. Alright, that's it for today. In the next video for concurrency theorems, we will discuss about ascribed circles, okay, and X center. Okay, all right, thank you very much.